السلام عليكم ورحمة الله. النهاردة هنكمل كلامنا عن يونت 8 والماتيريال اللي احنا كنا بناخدها في يونت 8 عن الأسيد بيز equilibrium. So let's continue what we were saying. We are continuing unit 8 and the material we were talking about in unit 8. So this is unit 8, continue. And we remember what we were speaking about the common ions and the buffers. If you remember, we said that the buffers are solutions. This solution will resist the change in the pH, resist any changes in pH upon addition of small amounts of acid or base. If I added small amount of acid or bases, it will not be able to change the pH. Why is that? Because I have added the buffer. So it will prevent the pH from changing. So let's see sample question number 1, because sample question number 1 is asking about this definition. It's asking me, this is sample question number 1. Know the definition of a buffer is a solution that resists the changes in pH upon addition of small amounts of H+ or OH-. What is the content of the buffer? The buffer is made of one of two things. Either it contains a weak acid in addition to its conjugate base, so it's made from a weak acid added to its conjugate base, or it is made from a weak base that's added to its conjugate acid. So either a weak acid and its conjugate base, or a weak base and its conjugate acid. This is what are the contents of the buffer. But how can we make it? So how can I produce this buffer? The buffer, so this is the definition and this is the content. How it can be made? How buffer can be made? How the buffer can be made? The buffer can be made by adding mixing. By mixing a weak acid with its salt. Mixing a weak acid with its salt, or mixing a weak acid in excess with a strong base, or mixing a weak base in excess with a strong acid. So let's see the first type. How can I mix a weak acid with its salt? If you mixed a weak acid like HF with its salt, that's NaF, it's going to form what? It's going to form the weak acid that we wanted to find, which is the HF and its conjugate base. When the HF loses a proton, it forms a F-. So it reacts with water to form F-. So this one loses a proton to this one, and this one becomes H3O+. Where is the conjugate base of this acid? And this is its conjugate base. Why it's called a conjugate base here? Because it's going to accept the proton from the H3O+ and form the H2O. So I need to make the F-. So if you added HF with NaF, you will form the F-. So now you have the HF and the F-. This is the weak acid and its conjugate base in the same time. Number 2 is by mixing an excess of a weak acid plus strong base. So if I put a weak acid like CH3COH in excess with a strong base, I'm gonna form the CH3COONA, and you said there is excess from this one, so CH3COOH. So now we have the excess the weak acid and its conjugate base. The third method is by mixing an excess of a weak base plus strong acid. So if you have, for example, the weak base, the NH3, and you mix it with a strong acid like HCl, so you have formed NH4 plus, and you said there is an excess. So what remains also? NH3. So now you have the weak base and its conjugate acid. So these are the three methods of preparation of formation of the buffer. So let's see some examples on that. So now we are asking what are the various procedures that produce buffer. So the various methods that produce buffer. You said I will put equal volumes of KOH and HCl. No, we didn't say that adding an excess and equal volume of acid and base, strong acid and base produces. So this is wrong. The second option he has given us equal volumes of KOH and C6H. So I put 0.5 molar KOH and 1 molar of C6H5COOH. Let's see. This means that you have put a weak acid and a strong base. So weak acid and strong base. We said that we can put a weak acid and strong base, but just it should be in excess. So let's see. If this one I put it, it will form C6H5COOK plus C6H5COOH because there is an excess. So this one is fine. Number 3, how can you prepare? Number 3, how can you prepare? Is it another method is putting 1.0 molar of C6H5COOH and 1 molar of C6H5COOK. I can see a weak acid and its salt. So a weak acid and its salt. If I have a weak acid and its salt, so I have a weak acid and its conjugate base, so it is a good method. So again, a weak acid and its salt, excess of the weak acid and its strong base, and strong base, excess of weak base and strong acid. It's asking which of the following are buffers mixed with equal volumes of 0.1 molar HCl and 0.1 molar KCl. Is this making a buffer or not? No, this is not a buffer. Why this is not a buffer? Because this is a strong acid and its salt. The mixture does not contain buffer because there is no weak acid in it and its conjugate base, or weak base and its conjugate acid will be present. The second one, if I mix it equal volumes of 0.1 molar HF and 0.1 molar KF. If I mix it equal volumes of this one, yes, this is a weak acid and its salt. So the weak acid and its salt, the weak acid has HF, and now I have the F minus. HF and its minus, F minus are the weak acid and its conjugate base, so they make a buffer. Yes, this is a buffer. Another one more example is if I put 1.1 molar of Na2HPO4 and 0.1 molar of NaH2PO4. Na2HPO4 and NaH2PO4. I can see that this is a weak base. So this is a weak base. Yes, this is a weak base, and this is a weak acid. This is a weak base, and this is a weak acid. So they form the conjugate weak base and its conjugate acid. If this is a weak base, it will take one extra proton. It will take one extra proton. It will form the NaH2PO4. So it will form its conjugate acid of this base. So weak base and its conjugate acid. So this is a buffer, correct answer.
So how does the buffer work? The buffer works because it has two components inside it. One component will prevent the attack of the hydrogen ions, and the other component will prevent the attack of hydroxide ions. We have hydrogen ions and hydroxide ions. So for example, if I have a buffer which is made from HF and F minus, that's a weak acid and its conjugate base. If I added H plus, what will react with it? The H plus will be reacted with the F minus from the buffer, form HF. And HF is a weak acid, so it does not change the pH. So what happened here? The H plus is neutralized. The H plus is neutralized, and the solution does not change its pH. What if I added to this buffer, if added an OH minus, then the other part, so this is the HF, and HF and the F minus. Then the H here is added, the F minus is going to work with it. If OH minus is reacted, then the HF is going to react with it to form F minus and water. So it's neutralized, so the OH minus is neutralized and there is no effect of adding the OH minus. So let's see an example. If I have a weak base is conjugate acid buffer, NH3 and NH4 plus buffer here. If added H plus and if added OH minus, what happens? Again, the buffer is made from two parts. It's made from the NH3 and its NH4 plus component plus it. So if I added H plus, it's going to react with the NH3 to form NH4 plus. This is a salt. So H plus is neutralized. And if I added OH minus, it's going to react with the NH4 plus part to form NH3 plus water. So the OH minus is neutralized. So every buffer has two parts so that it can react to the increase in the H plus or the increase in the OH minus solution. Let's see a sample question about that. Let's see a sample question about that and see if we can answer it. The sample question is asking if I have buffer CH3 COOH with CH3 COO minus buffer, how it works if I added few drops of HCl or if I added a few drops of sodium hydroxide. So again, the buffer is made from two parts. If I added HCl, so H plus to the buffer, the H3 part of the buffer is going to react with it to form CH3COOH. So what happened is the H plus is neutralized and there is no effect of adding it. If I added OH minus, the CH3COOH is going to react with it to form water and CH3COO minus. So the OH minus is neutralized. So there is no effect of adding the H plus or OH minus on the solution. Now, how can I know the pH of buffer solution? How can I know pH of a buffer solution? The buffer solution has a pH that can be found using the Henderson-Hasselbalch equation. Henderson-Hasselbalch equation. For example, if I am asked to prepare a buffer with pH is equal to 7 using a solution of 0.1 molar CH3COOH and CH3COONA, and the Ka of this weak acid is equal to 1.8 multiplied 10 to the power of negative 5. In this equation, I have the pH of the solution that I need to make using two solutions, 0.1 molar and 0.1 molar of the acid and its salt or its conjugate base. So pH is equal to negative log Ka. You know the equation of the Henderson-Hasselbalch equation. pH is equal to pKa plus log concentration of the conjugate base over the concentration of the acid. So conjugate base over the weak acid. 7 is equal to 4.74. So 7.4, how did we find it's 4.74? We got the pKa from the Ka by negative log. So negative log of 1.8 multiplied 10 to the power of negative 5 is 4.74 plus log the conjugate base concentration over the weak acid concentration. So 2.26 equal to the log of this one. If you want to get rid of log of both, so we will make anti-log for both sides. So 10 to the power of 2.26 equal to this concentration. We'll say that this volume is volume 2 and this is volume 1. Since the concentration is the same, so we'll say the ratio is for the volumes is the same. So since concentration of both is equal to 0.1, I will say V2 over V1 equal to 181.97. Let's say that both of them make a volume of 1,000 milliliters. So we can say V1 plus V2 equal 1,000 milliliters. We can say that V2 is equal to 181.971 volume, right? By multiplication of these two together. If we multiply these two together, we'll get this equation. So I can remove the V2 from here and say V1 plus, instead of putting V2, I will put 181.97 V1 equal to 1,000. So 182 by adding V1 plus 181.97 V1, 182.97 V1 equal to 1,000. V1 equal to this value and get it 5.47. So you need to put 5.47 from the V1, which is from the acetic acid, the weak acid, and put the rest of the amount, 994.53 milliliters, from the conjugate base of it. Now we'll say that we found the buffer pH if the base concentration over the acid concentration, which is the conjugate base over the weak acid, is constant, the pH is unchanged. The pH is unchanged. So if I change the concentration of the base and the concentration of the acid, but the ratio of the base to the acid is constant, then the pH will be constant. So if I make any dilution, has no effect on buffer. Dilution has no effect on buffer. Why dilution has no effect on buffer? Because it dilutes this concentration and dilutes this concentration, so the ratio is the same. The ratio is the same. The next question is asking us to find the pH of a buffer solution. So pH of buffer solution that made from 0.2 molar of NaF and 0.3 molars of HF. Again, the buffer pH is equal to negative log of the Ka. So negative log of the Ka or the pKa plus log the concentration. What did we say? The concentration of the conjugate base over the weak acid concentration. So negative log of the pKa, which is given as 7.2 multiplied by 10 to the power of negative 4. So negative log of 7.2 multiplied 10 to the power of negative 4, that's equal to 3.14. And the concentration, the log of the concentration of 0.2 over 0.3, that's equal to negative 0.18. So the pH of the solution will be 2.96. So if I prepare the buffer by making the weak acid and its conjugate base, its pH will be 2.96. I have one more question on the buffers. on the ratio is question 3 here. Calculate pH of the buffer when 0.4 and 0.6. If you see the other ratio was 0.2 and 0.3 and the buffer become 2.96. Here, if I calculate it with the same equation, it will be also 2.96. So the pH remains the same as long as the ratio is the same. The ratio of the concentration of the base, the conjugate base, to the concentration of the weak acid is the same. So since the ratio is the same, so the pH of the buffer is going to be the same also. Now we are going to talk about something called the buffer capacity. What is the buffer capacity? The buffer capacity is the ability of the substance called buffer to be able to withstand the changes in the H plus or H minus concentration. So how much it can take H plus and OH minus without change or big change in the pH. The larger the concentration of the weak acid and the concentration of the weak base, the higher the capacity. So the ratio of base, conjugate base to weak acid concentration equal to 1 give the best capacity. Why it's 1? Because the ratio is close to each other, it's high ratio. Equal to 1 is more important than the higher concentration. So the ratio bigger than 1 is more important than the higher concentration of the compound. When I choose an acid to make a buffer of a given pH, the pKa of the acid must be as much as can equal to or close to the required pH. So, for example, I have a question which is asking me if I have, this is the question, let me write it down. So if I have a buffer solution to be prepared, let me write it down. So this question is saying you wish to create a buffer solution with pH of equal to 5. Which of the following will be the best choice to prepare the required buffer? The first is HCl, and I don't use HCl because HCl, the Ka is very large, so the pKa is very negative, very small number. Now, when I see the second one, that's H3ASO4, Ka is equal to 5.5 multiplied 10 to the power negative 3, so pKa is equal to 2.3. And then number 3, the CH3COH, the Ka is equal to 1.8 multiplied 10 to the negative 5. So pKa is equal to 4.7. HCN is the last one. The Ka is equal to 4.9 multiplied 10 to the negative 10. So pKa is equal to 9.3. So the best one to choose is choose this one because this one has the pKa closest to the pH value. So I would always choose a pKa that the acid is equal to, is a little bit very close to the pH that I need to prepare.